Welcome to my classroom. This time, I talk about a magic show. Wow! Yes, I wish I could perform the magic show to you, but I need an assistant and we need to interact with an audience. The setting of this video does not allow, but I can talk about the magic. Anyway, see if you can get the idea of the trick before you move on for my explanation. There are variations of the magic show for further exploration. Wish you enjoy. Show time! Ladies and gentlemen, welcome to the magic show. Our magician David and his assistant Sarah. A volunteer is invited from the audience to check and shuffle a pack of pocket cards. The volunteer is asked to select 5 cards randomly and pass them to David without showing the content of the cards to others. David chooses a card to hide and displays the other 4 cards in a row. He then exercises his magic power by saying "Molly Molly home" and asks Sarah to read his mind. From a pack of 52 cards and 4 cards displayed, there are 48 cards left. It is not likely for Sarah to get the answer by wild guessing. Yet, bingo! Sarah gets the correct answer. Bravo! How does Sarah read David's mind? What is the magic power? You may pause the video and think about it. A card contains 2 information, the suit and the number. How does David pass the information of the hidden card to Sarah so that she is able to tell the answer? There are 4 suits of the pocket cards: spades, hearts, clubs, and diamonds. For each suit, there are 13 numbers from 1 to 13. It is easy to determine the suits by the pigeonhole principle. For any 5 cards in 4 suits, that is, 5 pigeons in 4 holes, there is at least 1 hole containing more than 1 pigeon. In other words, David must find 2 cards of the same suit. David takes out the 2 cards of the same suit, hide one and display the other as the first card so that Sarah can tell the suits from the first displayed card. Now, the number of the hidden card. After removing 2 cards of the same suit, there are 3 cards left. Compare the cards and regard them as small, middle, and large, according to their suit. Usually, we say spades greater than hearts greater than clubs greater than diamonds. Example, spade 3 is greater than diamond 9. If the cards have the same suit, then compare the numbers. Example, club jack is greater than club 4. To arrange 3 cards, there are 3 factorial, that is 6 permutations. Label these 6 permutations by numbers 1 to 6 like. That is, using the arrangement of the 3 remained cards, David can pass a number between 1 to 6 to Sarah. Besides the first displayed card, there are 12 choices left for the hidden card. How to settle this problem? Use the difference between the numbers of the hidden card and the first displayed card. If we put 30 numbers on a circle, we can see that, using suitable orientation for subtraction, the difference is always less than or equal to 6. Let me show this with 2 examples. Example 1. 2 and 6. 6 minus 2, 4. The difference 4 is less than 6. Example 2. 5 and 12. 12 minus 5, 7. The difference 7 is greater than 6 that we don't want. Let us reverse the order of subtraction. 5 minus 12, negative 7. It is congruent to 6 mod 13. The adjusted difference is within the range. In both examples, the difference is always lying between 1 and 6 and can be represented by a suitable permutation. In the first example, counting from the smaller number, adding the difference 4, the larger number is obtained. In the second example, counting from the larger number, taking the difference 6 steps, the smaller number is reached. In this way, David used the remaining 3 cards to pass a number for the difference or the number of steps to Sarah to link up the numbers of the 2 cards in the same suit. Let me summarize the idea. From 5 cards selected by the volunteer, there must be 2 cards of the same suit, so the suit of the hidden card can be identified. To find the number of the hidden card, let D be the difference of the greater number minus the smaller number. Then, there are 2 possible cases for the range of D. Case 1. D is less than or equals to 6. Hide the card of the greater number and display the card of smaller number as the first card. Arrange the remaining 3 cards to show the difference D. David's job is done. For Sarah, she knows the suits by looking at the first display card. Using the coding system shared with David, convert the next 3 display cards to a number between 1 to 6, that is D. Add D to the number of the first card. The sum is less than 13, and it is the number of the hidden card. Sarah gets the answer. Case 2. D is greater than 6. Basically, reverse the idea of case 1. Hide the card of smaller number and display the card of greater number as the first card. Reverse the order of subtraction, using the smaller number minus the greater number. For this negative number, take mod 13 to get the adjust difference, which is between 1 to 6. Arrange the remaining 3 cards to show the adjust difference D prime. David's job is done. Sarah sees the suits of the hidden cards from the first display card. Convert the next 3 display cards to a number D prime. Add D prime to the number of the first display card. This time, the sum is greater than 13. Take mod 13 for the number of the hidden card. Sarah gets the answer. The work is done. Let me use an example for a clear demonstration. Let the 5 selected cards be spade 3, hearts 5, club 2, diamond 3, and diamond queen. Diamond occurs twice, so take out diamond 3 and diamond queen. Queen refers to 12. 12 minus 3, 9, which is greater than 6. That is out of range. So reverse the order of subtraction. 3 minus 12, negative 9. Take mod 13. The adjust difference is 4. David hides the smaller number, that is diamond 3, and displays diamond queen as the first display card. Arrange the 3 remaining cards for the adjust difference 4, which is middle, large, small in our coding system. So, next to diamond queen, David puts heart 5, spade 3, club 2. David's job is done. Sarah looks at the 4 display cards and knows that the suits of the hidden card from the first display card, that is diamond. From the arrangement of the next 3 cards, middle, large, small, it represents the number 4. Add 12 by 4, 16, greater than 13. So take mod 13 and get 3. That is, the number of the hidden card is 3. Therefore, the hidden card is diamond 3. Bingo! We see that the magic power comes from the pigeonhole principle and the modular arithmetic. In the magic show, to guess 1 card, we need to select 5 cards and display 4 cards. If we want to guess 2 cards, at least how many cards are needed to select? Using the previous result, 10 cards can do the job, but we want the least number of selected cards. Take 1 card less, say Select 9 cards and display 7 cards. By pigeonhole principle, for 9 cards in 4 suits, there are at least 2 pairs of cards of the same suit, right? You may check this out with a worst scenario. So, the first 2 display cards are used for showing the suits, and 5 cards left for arrangement. According to the previous discussion, to guess the number of a hidden card, we need a number ranging from 1 to 6. So, 6 choices for the first hidden card, and another 6 choices for the second hidden card. By multiplication principle, 6 times 6, 36 choices for the pair of differences of 2 cards. To tell the choice, we can arrange the 5 remaining cards. 5 factorials, 120 permutations. The number of permutations is greater than the choices of the differences. It works. So, 9 selected cards can tell 2 hidden cards. Can we trim the selected cards further? That is, can 8 selected cards tell 2 hidden cards? After 2 cards are hidden and 6 cards left. Like the previous discussion, 2 cards are used for showing the suits, and 4 cards are remained. 4 factorial, 24. That is, 4 cards give 24 permutations. But there are 36 choices for the pairs of differences. Not enough permutations. Wait. Let us think more carefully about the choices need. If we place an additional requirement to the pairing of the differences, we can reduce the number of choices. Say, compare the 2 differences and place a smaller difference before the larger one. Let me show this with a table. The smaller difference and the larger difference. Of course, the 2 differences can be equal. Thus, the choices include one on the diagonals and in the upper triangle. In this way, the number of choices equals 21, which is less than 24. So, it works. 8 selected cards can tell 2 hidden cards. The number of cards cannot be further reduced to 7 cards. For 7 selected cards, only 3 cards are left for arrangement. That is, only 6 permutations can be provided, which is not enough to indicate the differences of 2 hidden numbers. Therefore, to guess 2 cards, we need to select at least 8 cards. Let us review what we have found. In the magic show, there is 1 hidden card for guessing. We select 5 cards from the pack of 52 pocket cards. When 1 card is taken away, 4 cards are displayed. In order to guess the hidden card, 1 card is used to show the suit. Therefore, 3 cards are left for arrangement to form a number. To arrange 3 cards, there are 6 permutations, that is, choices of arrangement. To guess the number of the hidden card, the range of the difference is 6. For the first variation, we hide 2 cards for guessing. The least number of selected cards is 8. That is, there are 6 displayed cards. 2 cards are used for finding the suits of the hidden cards. 4 cards are left for arrangement for a number. 4 factorial is 24. 24 permutations can be formed. There are 2 differences involved. Pair them up, should be 36. But we put the smaller difference first and reduce the number to 21. Now, the further extension, we hide 3 cards for guessing. How many selected cards are needed? Similar to the first variation, it is easy to see 3 cards are used for showing the suits of the hidden cards. If we use 5 cards for arrangement, there are 5 factorial, 120 permutations. If we use simple multiplication principle for the choices of the 3 differences, 6 times 6 times 6, 216, larger than 120. If we use the adjusted number for the two differences, 21 times 6, 126, still larger than 120. Yet, can adjustment be made for three differences? The answer is yes. Actually, 11 selected cards are enough for guessing 3 cards. What is the number of actual choices needed for 3 differences? I leave this part for you to fill in. Originally, I planned to have another variation which is in different direction and challenging, but it takes more time for discussion and makes the video lengthy for uploading. I leave this variation to the next video and we'll talk about what message we can draw from the magic soul and their variations. Anyway, hope you find the magic soul interesting. You may discuss and work with a friend to perform the magic soul to your friends as an educational entertainment. Wish your audience enjoy your performance and appreciate how simple mathematics works for mind reading.